In this video, we'll be talking about what we mean by strong acid, strong base, weak base, as well as the concept of polyprotic acids and polyprotic bases. A little bit of background. Acid-base reactions, you should essentially think of them as just another type of equilibrium. The same equilibriums that we've been working with in the past, where you have an equilibrium constant that is the products divided by the concentration of the products divided by the concentration of the reactants raised to their respective coefficients. Again, leaving out any pure liquids or solids. So if we have our reaction for an acid, we have some acid that has an acidic proton here. It can react with water to form a hydronium ion, H3O+, as well as the conjugate base to our acid. So the products are going to be your hydronium ion, H3O+, and the conjugate base. Those go on top. Each one of these has a 1 for the coefficient, so it's raised to the first power. On the bottom, we have our acid, but we leave out water, just like we do in equilibrium. And the reason we're leaving the water out is because it's a liquid, and so the concentration of water doesn't change. And so it can be considered a constant and gets lumped in with our equilibrium constants. Now, the terms strong and weak, when we're talking about acids, are used to represent or to give an idea of the size of the equilibrium constant. When we say something is a strong acid or a strong base, what we're essentially saying is that the equilibrium constant is large, meaning that the reaction proceeds a good portion towards the products. Generally, the reaction goes almost completely to the products. In the case of a weak acid or weak base, those ones, the reaction doesn't go all that far, meaning that the majority of our acid is going to stay in the acidic form, and only a little bit of it is going to be converted into the conjugate base by donating the acidic proton. The term strong and weak are used to indicate how easily an acid or base gives up or accepts that acidic proton. So, a strong acid is a strong electrolyte, meaning that it will break apart, giving us a lot of ions which can shuttle charge around in an aqueous solution. It enables it to conduct, or it enables the solution to conduct electricity well. Practically all of the acidic molecules will ionize. This is because you have a large K value. The conjugate base will be a weak base. For a strong base, it's also a strong electrolyte, because the term strong means that the equilibrium constant favors the formation of the products. So practically all the base molecule will form hydroxide ions if it's in an aqueous solution, either through dissociation itself, in the case of like sodium hydroxide, NaOH, or it will react with water to accept one of the hydrogens from water to give you a hydroxide ion. In either case, it's going to have a large K value. When you have the base on the other side, you have the conjugate acid. If you have a strong base, then the conjugate acid will be weak. There will be a very little driving force for that conjugate acid to donate the acidic proton to go back to the strong base form. On the flip side, if you have a weak acid, the term weak, when we're talking about a weak acid, means that it has a small K value. Because it has a small K value, the reaction doesn't proceed very far towards the products, so it won't be a strong electrolyte. It doesn't break up into its constituent ions, and so it's not able to shuttle charge from like an electric current. So only a small percentage of the molecule will ionize, which essentially means that it has a small K value. For a weak base, the exact same idea. Only a small percentage of the base molecule will form hydroxide ions, either again through dissociation or the reaction with water. These are indicated by small K values, very small equilibrium constants. So for a strong acid, to see an example of one, strong acids will donate practically all of their their acidic protons. So you'll see virtually 100% ionization in water. They're very strong electrolytes. So when we tell you the concentration of an acid, of a strong acid, so let's say we have a 1 molar hydrochloric acid solution, that means you can think of it as essentially having 1 mole per liter of the hydronium ions, right? So a 1 molar hydrochloric acid solution, we can think of that as being the equivalent of 1 molar of H3O plus. So conceptually, looking at atoms sort of in a beaker, if we put HCl into water, it's going to completely break up into chloride ions, Cl minus, and forming hydronium ions when it reacts with the water. Looking more at ball and stick type fashion, the green is the chloride ions, the white is the hydrogen. When we put it into solution, you get chloride ions formed and then H3O plus in solution. For a weak acid, like hydrofluoric acid, it doesn't disassociate all that much. Very few of the HF ions will actually break apart to donate the acidic proton to, in this case, water. So weak acids donate only a small fraction of their acidic protons. Most of the weak acid molecule doesn't donate that acidic proton to water. It stays in the acid form. In the case of HF, the vast majority of it will be HF. Very little of it will form the conjugate base by donating the acidic proton. So most of it will be HF. Very little of it will be in the F minus form. What that means is if we put it into solution, the concentration of the hydronium ions, the H3O plus, will be much, much less than what we report as being the concentration of the acidic solution. So a 1 molar concentration for HF, right? The concentration, if HF is 1 molar, then the concentration of our hydronium ions, our H3O plus, is going to be actually much, much less than 1 molar. If we take a look at what that looks like in sort of a more conceptual form, we have our HF as our acid. We put it into water. You can see that the vast majority of it stays in that HF form. Right? Most of this is as HF. Only a couple of the fluorines or the hydrofluoric acid will give up its acidic proton to form the fluoride ions. The vast majority of it stays in the HF form. Now, some substances have more than one proton that can easily come off, right? Because any hydrogen has the potential to be donated as an acidic proton, and that again depends on the strength of the interaction holding the hydrogen onto the molecule. Again, as we said when we were talking about the sort of the definition of acids and bases, carbon-hydrogen bonds are particularly strong, and so they're not generally considered to be acidic protons, right? The bond is strong enough that the hydrogen will stay attached to carbon. However, when a hydrogen atom is bound to an oxygen, those are fairly weak bonds, and a lot of times the hydrogen that's attached to an oxygen can be donated and act as an acidic proton. So for some compounds, they will have more than one hydrogen that can act as an acidic proton. The group that we've been talking about before, where only one proton was being donated, those are called monoprotic acids. Mono meaning one. So a monoprotic acid is one that only has a single proton that can reasonably act as an acid. For those molecules that have more than one, so two or more protons that can be donated, they are called polyprotic acids. Poly meaning many. So a polyprotic acid is one that can donate 2 or more acidic protons. We can also have bases, right, that can accept 1 or 2 or more protons, right? So a monoprotic base is one that has the ability to accept only 1 proton. A polyprotic base is a base that can accept 2 or more protons. So an example of this would be H2SO4, right? H2SO4 actually has 2 acidic hydrogens, right? So the Lewis dot structure is a sulfur in the middle bound to oxygen, and 2 of those have acidic protons attached to them, right? And so because the hydrogen here is attached to an oxygen, these are weak bonds. That one's a fairly weak bond, and this one is also a fairly weak bond. So H2SO4 has the ability to donate 2 acidic protons. So it will first donate 1. The majority of the H2SO4 will donate 1 proton before any of the ones that have already donated 1 will donate a second. So your first reaction is H2SO4 will donate 1 acidic proton, giving you HSO4 minus and that acidic proton. And then once all of the H2SO4 has been converted into HSO4 minus, then some of those HSO4 minuses can start giving up the second proton to form HSO4 2 minus. We could also have something like the phosphate ion, PO4 3 minus, which can first accept 1 hydrogen. Once all of your PO4 3 minus in solution have accepted a proton, then those that have been converted into the HPO4 2 minus can accept an additional hydrogen, forming H2PO4 minus. Once all of the HPO4 2 minuses have accepted a proton, forming H2PO4 minus, then the H2PO4 minus can accept one last hydrogen atom or proton to become H3PO4. So in this case, this would be a polyprotic acid. And this would be a polyprotic base. Now, because of the nature of acids and bases, when an acid gives up a hydrogen, you form its conjugate base. So HSO4 minus is the conjugate base to H2SO4, but it's amphoteric. It can either accept a hydrogen to go back to be H2SO4, or it could donate its remaining hydrogen to become HSO4 2 minus. So because at the end of the reaction, an acid forms the conjugate base, and if we have a polyprotic acid, that second, the conjugate base to the first acid can itself act as an acid to form a conjugate base. In the reverse direction, right, the ultimate conjugate base is also a polyprotic base. Similarly, this H3PO4 would be a polyprotic acid. It has 3 acidic hydrogens that it can donate going in the reverse direction. A couple of examples of what we consider strong acids. Those again are ones that will give up all of their acidic protons are hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, nitric acid, HNO3, perchloric acid, HClO4, and sulfuric acid, H2SO4. Of these, it would be a good idea to at least have memorized that these three and these two are strong acids. The perchloric acid, this one, doesn't get used a lot. It's a less common strong acid, but nitric acid, sulfuric acid, and then particularly the hydrochloric, but also the hydrobromic and hydroiodic are fairly common acids that can get used. Some weak acids are hydrofluoric acid, acetic acid, which is what you find in vinegar, formic acid, sulfurous acid. The difference between sulfuric and sulfurous acid is that this has 3 oxygens, whereas this has 4. Carbonic acid and phosphoric acid, right? So our sulfurous acid is a diprotic, a polyprotic. In this case, di means 2. So we can further refine the idea of a polyprotic acid with di or tri if it has 2 or 3 acidic protons. But primarily for our course, we'll be just referring to it as a polyprotic acid. Okay. Now, in terms of the strength of acids and bases, right? Commonly, the acid strength is measured again by determining the equilibrium constant of the substance's reaction with water. If a substance reacts with water strongly, i.e. the equilibrium very much favors the formation of the acid and the hydronium ion, right? Giving you very little to none of the original acid remaining in solution, then we call it a strong acid. These are typically ones where the conjugate base doesn't really have a very strong pull towards the acidic proton. Another way of thinking about that is that the conjugate base is a very stable anion, a very stable negative ion, meaning that it doesn't really need to pull on an additional proton to stabilize itself. The further the equilibrium position lies towards the products, the stronger the acid or base is going to be. And that position of the equilibrium depends on the strength of the attraction between the base form and the hydronium ions, or the proton, in solution. The stronger the interaction, or the stronger the attraction, the stronger the base and the weaker the acid. Finally, some general trends in acidity. The stronger the acid is at donating the acidic proton, the weaker the conjugate base is going to be towards accepting it. The stronger the base is, the weaker the conjugate acid will be. We'll be going into greater detail on this in a later video, but generally, for what we will call oxyacids, those are acids where the acidic proton is bound to an oxygen atom. The greater the oxidation number on the central atom, i.e. the more oxygen there is bound to that central atom, the stronger the oxyacid will be. Right? So if you remember back when we were just looking at the relative strengths or categories of sulfuric versus sulfurous acid, H2SO4 versus H2SO3, the H2SO4 was considered a strong acid, right? Whereas the sulfurous, H2SO3, was considered a weak acid. The main difference between the two is the sulfuric acid has 4 oxygens and the sulfurous has 3. Similarly, HNO3 versus HNO2. HNO3 is a strong acid, whereas HNO2 is a weak acid. The cations are stronger acids than neutral molecules, and neutral molecules are stronger acids than anions when all other things are the same. So if we look at the hydronium ion versus water versus the hydroxide ion, each one of those still has 1 or more hydrogens that could be theoretically donated, right? But the hydronium ion, H3O+, can easily donate that extra proton to go to water. Water is less strong of an acid than the hydronium ion is, and the hydroxide ion is a very, very, very weak acid. In fact, it's not really acidic at all. Similarly, ammonium, NH4, versus ammonia. The ammonium, NH4 plus, is a much stronger acid than NH3. A way that you can think about why this is as the proton comes off of something that has a positive charge, there's no real attractive force to hold it on. However, if you have something that is neutral, such as your ammonia, NH3, and it's going to NH2 minus, you have NH3, which goes to form, it's an equilibrium, so H plus plus NH2 minus. They have opposite charges, the proton and the NH2 minus, and so there's electrostatic interactions that are going to try to pull these two together. So having this hydrogen come off and go away is going to be a little bit difficult because of the attractive force of the opposite charges. If you don't have opposite charges, then there's no attractive force. So if you have your NH4 plus giving off a hydrogen, you're left with NH3. The NH3 is neutral, and so there is no attractive force or no electrostatic attractive force that's pulling this proton towards the ammonia, right? So that's why the NH3 is a weaker acid, because the acid has a harder time going away from the conjugate base, whereas NH4 plus is a stronger acid because there's no attractive force between its conjugate base and that acidic proton. Right? So what this means is that each sequential proton or acidic proton that comes off for a polyprotic acid will become less acidic, because each proton that comes off will make the corresponding conjugate base have a more negative charge on it. The trend for bases is the exact opposite, right? As the charge goes up or becomes more positive, it becomes a weaker and weaker base.